what are we doing today? We're talking more about forces. Let's check it out. Does your bathroom scale measure weight or mass?
Huh. In an elevator.
Ground floor. Look at those shoes. What does that say?
100. Hold still, damn it. 124.
Oh, look at that. Okay, predict what's going to happen when the elevator goes up. Explain your prediction. Does it fit your prediction?
So pause this, make a prediction, think about it.
Yeah.
Now, at the start, when the elevator first starts going up, what is that, 130?
124 to start off with.
124 now.
Oh, yeah. He's going up now. Oh,
118.
yeah.
Did he lose weight? What happened?
Okay, fourth floor, 124 still. Yep. 124.
Now it's going down. Stop it. What's going to happen at the start, in the middle, and at the end?
How will the weight change? How will the reading change?
Huh.
So 124 is what it says now.
Come here.
Come on. Go.
Oh, 118. I wish that was that easy for me to lose weight. 124.
And brakes.
130. What the deuce is going on here? I'm going to go turn the lights on.
What's going on here? How can you lose weight?
I know.
Tell me your secrets. I'm just kidding. I don't lose weight. I feel great about my body. Okay, moving on. Confidence is key. Okay. So we just watched a video. Not entirely sure what's going on there. Let's take a step back and look at some things that we know. Net force means two things. This is really important, actually. The first thing that it means is it is the vector sum of all forces.
Oh.
Net. Is there
Net.
another word for this?
What does net mean?
Net could mean like the total or the sum,
I like
adding it all together, right? It could be one or two or more forces.
Yep.
Okay, so this is one idea of net force. This is going to be super important as we go forward in today's lesson. But there's another definition. Net force is also, an applied net force causes a mass to accelerate. So when you apply a force, our acceleration is up and our mass is going to be moving.
What? That's one of them laws, isn't it?
Yeah, it's familiar, right? This isn't even second law. We know this one. This is familiar. This is review. So we have to take what we've already learned plus something new that we've learned, and we're going to piece some stuff together here. Weight is the force of gravity pulling down.
You should know that already.
Yeah, and this is basically the force of gravity, right?
Yep.
Negative 10 meters per second. Right here, right? Times your mass gives you the force.
What determines how much weight you got?
How much mass you have.
There you go.
Right, because the G is always the same. And it's always down. Oh, new word alert. The normal force, we call it Fn, is the force exerted by a surface perpendicular to the surface at a point. What does that mean? In this first picture, we have the force of gravity pulling the dog chow, the doggy foodies, down, right? And what force is pulling it up here?
Force of the hand.
Force of the hand, okay? Now, change scenes here. This person's no longer in the picture. We have table here now, force of gravity pulling it down. What's pulling it up?
The table looks like it's about to break.
Yeah, the table, right? So the table exerts a force on the dog food up, and the gravity exerts a force on the dog food down.
And that
keeping
force
it
up
there.
we call the
Normal force.
Sweet.
It's important. Okay. Whew. All right, challenge. Can you read through this question? Through this sentence? I'm already losing my mind. Can you read through this sentence and stay focused the whole time?
Ready, Mark? Get set, try.
Okay, my turn. In a non-accelerating horizontal system, the normal force is equal in magnitude and opposite in direction to the force of gravity.
Ah.
Let's go take a look at the book now. Page 91. Okay, so here we have this table, and we have two forces that are acting on this block. We've got the force, what do we want to call this?
The weight, the force of gravity.
Weight, or this is important, weight or the force of gravity, okay, same thing, pulling down, in this case, because we're on Earth, pulling down, and then we have the normal force pushing up. And you can see that they are equal in magnitude, but opposite in direction, yes? Beautiful. If acceleration occurs, there is a net force.
Okay.
Okay, so let's see. So if there is, let me take a look at my notes here. Oh yes. So if these two are equal, if my weight and my normal force are equal, if they're the same, then we're not going to have any net force, right? Zero.
Like on this book right here, it's just sitting there.
Yeah, the force of gravity pulling down and the normal force pushing up is zero. It's just chilling, right? It's not moving.
That's right. The
Okay.
net force would be.
It would be zero.
That's right.
Right? It's in acceleration is zero. Now let's talk about how we know what the direction of the force would be. If this one is bigger than this one, then the net force can be this way, right?
That makes sense to me.
And then if this one is bigger than this one, the net force would be that way, right?
That makes sense too.
And what do we know about the direction of the acceleration compared?
It's always the same as the direction of the net force.
Yeah, so if the net force is this way, the acceleration is also that way.
Yeah.
And vice versa. Okay. And what do we have going on here? Well, this is that.
Newton's second law.
Okay. This is that.
Definition of weight.
And then this is the same thing.
Yeah.
Okay, cool.
The force
All
of
right.
the table.
This is so important. Now remember, this is what the second thing this is that second definition of net force. Right? The force net, or sorry, it's the first one. The force net is this one plus this one.
That plus means it's a sum.
Yeah, adding together.
I like that.
Okay. All right. Let's do a lab to observe a vertically accelerating system. Oh, because we were talking previously about a non-accelerating horizontal system, but we don't care about that. We're changing things up here. Oh, wrong, too far. Okay, we want to know about a vertically accelerating
We're going to do
system.
some acceleration. Do they have a lab sheet?
They do. I'm thinking that I'm probably going to put this on the next page in Canvas. So, or actually, I'll add it to the bottom of this this video. So
So
it'll
we'll
be there
do the
for you.
procedure. They need to do the lab.
Yes, exactly. Okay. So it says, lift the mast from the floor to 2 meters above the floor. Ooh, nice.
Yeah, we'll find
you
out
see
how
me?
nice it is.
Good. Am I good right there?
Whoops.
Yeah, right.
What could possibly go wrong?
1.5. Right.
Yeah, we're just going to have to get back. I'm going to do this.
Oh yeah. Okay. Boykin is going to be my starter and stopper. Hopefully he does a better job this time than on the hacksaw lab. Okay, so we're going to lift the mast from the floor to 2 meters above the floor. Yep. Your goal is to describe the direction of the acceleration of the mast. You ready?
Go. Sweet.
Nice. Nailed it. Okay. So
we're doing this, right?
Mm-hmm. So describe the direction of the acceleration of the mass at the start when it was on the floor,
Yeah.
and the middle when it was kind of in the middle, and at the end of the trip, way up here, 2 meters above the
So it
ground.
was on the floor. It wasn't moving,
In the middle, and at the top when it
and it had to come to a stop at the top.
yeah, when it was moving too. And then this is our graph that we got. Oh wait, do we want to? Oh yeah. Okay. And we'll do this part first. Describe the direction of the acceleration.
Okay.
Okay. Now, using the LabQuest 2, that's this, and the force sensor, which was this, record the force up or the normal force. You exert lifting the mass from the floor 2 meters. Okay. So sketch the graph. What's the normal force up top there? 8.33 newtons. So this is the normal force.
At when we first started, when we picked it up off the floor.
And it was 8.33 newtons. You might want to write that down somewhere. Maybe I should write that down. This little number. And then what was the other one, Wigan?
At the top, when you came to a stop, it looks like it was 2.07 newtons. And the mass is half a kilogram, 500 grams.
So sketch the graph. You guys see it, and this is, it's right here. That's what we're looking at mainly. That's before and after. Okay, when I was just chilling.
Here's before when it was just hanging, and then started going up, and then here in the middle it was coming up, and then here's where it stopped at the top, and then it was. So this is.
Ignore.
Well, no, that's the normal weight of the thing when it's just hanging.
Just chilling. Okay. Okay. Once you've drawn that, what does this graph mean?
So sketch that out. What the deuce is going on here?
Okay. All right, next step. Make the free body diagram of the forces acting on the mass at the start, in the middle, and near the end of the trip. They can do that, right?
Well, what's going to be the same every time?
Well, we know that the force of gravity, the force pulling down, is going to be the same every time, or the weight, right?
Yeah, and if it has a mass of half a kilogram...
The mass will also always be the same.
So if you know the mass, can you find the weight? Half a kilogram? Let's use 10 meters per second squared. We'll let them do that.
Okay. All right. And shall we take a look at my next thing?
Well, let's go back to this. But the gravity is the same every time. What's going to be different?
What's going to be different? Well, what do we measure on here? We measured the normal force, right? So what's going to be different is going to be my normal force.
Yeah.
Okay. Oh, sorry. Normal force at the bottom. What was at the top?
Yep. Is this anything like the YouTube video we saw?
Oh, yeah.
All right, now what's next?
Do we want to get a middle number there? Or
So go ahead and pause. Well, can we get a number in the middle? That's about... Here. Oops.
Pause.
We lost the data. No, we lost
we
it.
recorded it.
We lost the data. So, in the middle...
I think it was 5 point something.
Yeah, let's call it
Ignore
5.
it. Okay.
Call it 5.
We'll call it 5 newtons.
In the middle.
Okay.
All right.
What
now
next? We're like, what's next?
Sorry.
It's okay. Sketch a prediction of what the graph would look like on a trip from 2 meters down to the floor. So I'm not going to do it for you, but just so you get an idea, this is what I want. So now you're starting 2 meters up.
On your mark, set, go.
Ew.
Boom.
What would that look like?
Oh.
Okay. And then test your prediction using the LabQuest.
You want to do it?
Yeah, I guess we can do it.
Yeah, let's do it. Here, I'll set this
Let's
thing
get
up
set
again.
up again. It's always better the second time.
All right.
Okay.
So
When
we're
you're
going
ready.
to start up. And on your mark, get set, go.
Yes, that.
Well, that was a good one.
Oh my God, it's beautiful. Wow, this might be my best work yet.
Who is that masked man? That is
Wow.
good. So at the start, when you first started going down.
Okay, this
That
was when it
was-
was at the very top, right? It was at the top of
At the top, when you started going down, it was 3.3.
3.3. Shall I write that?
Why not?
Okay, so now the force at the top for normal was 3.3, you say?
That's when you dropped out from underneath it.
Yeah. Okay, force in the middle. Force normal, sorry, neutral.
I'm going to call it 5.
Okay, sweet. And then the
What?
normal force at the bottom.
8.73.
Oh, not bad. Pretty similar to what we got before, right?
Yep.
All right. Okay. Again, make the free body diagram so the force is acting on the mass. Include the force net and the acceleration.
What's going to be the same every time?
What's the same every time? The force, the weight, or the force of gravity down is going to be the same. The mass is going to be the same. What will be changing?
Well, you got the data, yes?
My normal forces. And then I say to include the net force. How could you calculate the net force?
Go ahead and give it a shot. We're going to pause this while you work on that.
Yeah. And the last thing you need to do is Google it. What is apparent weight? Or, even better yet, find it in the book.
In the book is a better idea.
Do you have your book yet? If you don't have your
I
book
think
yet, you
we're
should
in
find your
chapter
book.
4. I think it'd be in chapter 4. So pause, finish the lab, and then we'll come back.
And here we are.
And we're back.
Okay. Apparent weight. In a vertically accelerating system, like what we just did, this is the normal force.
Oh.
What? Acting on your mass causing the acceleration. Wait, okay, hold on. I think I just had a light bulb go off here. So in a vertically accelerating system, like on the elevator or like with that thing, the apparent weight is the normal force.
Acting on your mass.
Acting on your mass, okay, causing the acceleration. Oh, let's talk about this.
What the deuce is that?
You know, this kind of confused me the first time I looked at it, but it's really not that simple, not that hard. It is simple. Let's talk about where we get this from. So, let's go ahead and write this out. So, force net equals the force of the normal force plus
The weight.
the weight. Now, where do we get this from? We said the net force is the force of gravity plus the normal force equal in magnitude, opposite direction, right?
It's the sum.
It's the sum, right?
Yep.
This plus this gets you the net force. Now, in order to get that over there, we just do some simple math.
MA, MG, where'd that come from?
We know that the net force is m times a. Normal force is the normal force.
Whatever it is.
Okay, and weight is m times g, right?
Oh, yeah.
So let's just get this by itself. How do we do
get
that?
to this?
mg. mg. Oh, that shouldn't too bad. So it's just, I'm going to go and put this over here though. Fn equals ma minus mg.
OMG!
Oh, jizzle! And I forgot the arrows. Okay, so those arrows are super important.
The weight is always down.
Weight is always down
And
because
for
the force of gravity,
And the normal
all
force.
is always up. Okay, I think that explains that, don't you?
Yep.
Nailed it. Okay. Oh, make three free body. Miss Moore, I can't speak. Make 3 free body diagrams of the mass for the trip up.
They've already done this.
Start, middle, and top. You have. Let's check your work. Let's see how you did. What should this look like? All right. So start, middle, and top. Start, middle, top. Oh, and then 3 dots. 1, 2, 3. Okay. So what do we say was always going to be the same?
Force of gravity.
Force of gravity, also known as the weight. And that was m times g, right?
Yep.
So, the weight.
That's not going to change because it's still 500 grams.
Oh, gosh.
Half a kilogram.
Exactly. Okay, so it'll be the same thing for all of them. Okay. What else? What did we measure with the?
At the start,
What was
that
it?
was 8.33 newtons up.
Okay. What do you notice about this arrow?
It's blue.
Yes. Okay. At the middle, oh, draw to scale. And we said that was about 5, right?
Yeah. And at the end, it was 2.07.
2.07.
What's the weight? How can we find the weight?
Yeah, how can we find this? Mass times gravity. Do we know the mass?
It's half a kilogram.
Mass is half a kilogram, so let's see, 0.5 kilograms times the force of gravity, meters per second squared.
Half of 10.
Half of 10 is 5. Negative 5.
Negative 5.
Negative 5 kilograms meters per second squared, or newtons.
You also, I would write 5 kilograms up there. I put what the mass is right by the
right
dot.
here?
Yeah.
That's a good idea.
More information be more better.
Where should I put it at?
Next to the dot.
Oh, right here. Okay. Let's add mass. And you know what? I'm just gonna add it all the way across. It's helpful to see. The consistency. Ooh, that kind of rhymed.
You're
Bars.
a poet and you didn't know it.
Okay.
All right, so the weight's going to be the same every time, huh?
And the normal force is changing. What else do we have here? Can we talk about what direction the net force is going to be?
We can get the net force because that's a sum of the forces, isn't it?
Yeah. So one way of looking at net force is the force 1 plus the force 2.
Yeah.
Okay. So let's see. We've got a really big. We've got this
8.33
one.
up. Yeah.
Okay. So it looks like it's the net force is going to be up, right?
Yep.
Oh, let's just go ahead and put the arrow there. Up, like that. What about the net force here? Don't they cancel each other out?
Yep.
So, 0. Okay. Force net here. Well, there's more down, so
It's going to be down.
it's going to be down.
How
Okay.
can we know how much the net force is, though?
Oh, that's a good question. Okay, well, I think that we could do something like, couldn't we just add these two together?
That's what sum means.
Right? Okay, so we could do 8.33 plus a negative 5. I get 3.33. Newtons, which it makes sense. Yeah,
Yeah.
that makes sense. Okay. This one, nothing. Okay, 0 newtons. And then this one, well, can't we just do 2.07?
I'll put the weight on there. The weight,
Oh,
is,
shoot.
the weight is negative 5.
Yeah. Negative 5 newtons. And in case you forgot, that's from over here.
Yep.
Okay, so I can do 2.07. Oh. Get rid of that. Plus negative 5, and I get negative 2.93. Yikes.
Gotta get back in the gym. Sorry, you do not need to get back in the gym.
You don't want none of this.
That's
Okay.
right.
Okay, so now we've got the net forces. What else can we get?
What can we get if we got the net force and the mass?
Wait. So, force equals m times a. We have these two things.
We could find the acceleration.
Yeah, acceleration equals force over mass. Okay, so let's go ahead and do it. So my force here is 3.33 divided by 0.5. 3.33 divided by 0.5, and I get 6.66. Ooh. Okay.
6.67. We don't want to conjure up Satan.
Wait, what direction is my acceleration here?
Same direction as the net force.
Yeah, so my acceleration is this way, and we said 6.67 meters per second squared. Okay. Do we have any acceleration here?
Not if there's no net force.
No force means no acceleration. Nada. Okay. And then for my last trick, let's see. My net force is negative 2.93, and I divide it by my my mass, which is 0.5, and I get negative 5.86.
That'd be down.
Which makes, yeah, right? Acceleration here is down, and it equals negative 5.86.
Look at all that stuff we got out of just that little lab experiment that we did.
Well, we're pretty cool.
I'd say so.
Yeah. No? Is that everything? We good?
So if you don't have this kind of stuff on your free body diagram,
Add it to your free body diagram now.
that's what I'm saying.
And you'll have to make some changes for the second one, right?
Oh, we haven't done that yet.
Didn't they do the correction?
Oh, that's right. They
Yeah.
did it. So how could you make yours look like what we've got for the trip up, except for the trip down?
Well, what changed for the trip going down?
Yeah.
Right?
Yep. But the weight stayed the same.
Weight was the same. Okay.
And they've
also,
got these numbers over here.
Yeah. So make sure you plug these in and make it
Do the same thing we did.
for that second one. Okay. Newton's second law established the relationship that governs all acceleration. Force net equals mass times acceleration.
Es la ley!
An object has a true weight found thus. Weight equals mass times gravity, which points down. So when we talk about true weight, we're talking about this right here.
That doesn't change if you're not going off the earth.
The apparent weight is what shows on the bathroom scale, the normal force, which points up.
Let's see that bathroom scale thing again.
Let's do it.
I'll take a walk around the room while she's doing that. Not quite as smoky today. You guys remember the smoke?
How can you forget? Should we hit the lights? It's fine.
Yeah, I'll hit the lights.
Full screen. Okay, ready for this?
So the prediction is at the start, in the middle, the top. Hit it. Do you know the answer? We are in the elevator on the ground floor. 124 pounds. What's going to happen at the start, in the middle, and at the end, and why? I should let you say this. I'm up here blabbering away. Sorry.
And think about the 0.5 kilogram mass and what
Here we
we
go.
saw there.
Ooh, did he gain weight?
Okay, back down to 20.
He's still going up. He's still going up, but it's back at 124.
Oh, 118.
He lost weight.
And 144.
Does that have something to do with this? Hold still. Okay, so going down, what's the scale going to do?
What's going to happen to the scale? Blue.
It's changing colors.
Purple.
It's Roy G. Biv. When it gets to violet, we know we're getting close. Whoa, you lost weight.
118 to 124. Okay, cruising. Oh, 130. Wait.
It's kind of like our data over here, isn't it?
Yeah. Okay. Move this on over. Oh.
Oh, yeah.
Lights, camera, action. Okay. What were we talking about? These two weights are added together to equal the net force, which produces the acceleration. I think that we're talking about these two, right?
Yep. The actual weight and the apparent weight.
Okay, the actual weight and the apparent weight.
Which is the normal force.
Yeah. And they're added together, and we can use that to get the acceleration.
And that weight is what shows up on a scale. Because what this thing is that we were using is like a scale.
And it measures the normal force, just like the scale does. Practice problem. Should probably erase this, huh?
Yeah.
Okay, go ahead and read through the question. A 42-kilogram person is standing on a bathroom scale in an elevator that is going up with an acceleration of 0.5 meters per second squared.
Make a free body diagram.
Yeah. What does the scale read?
All right.
Okay. All right, so here is this.
What's the mass?
What is our mass? A 42-kilogram person is standing on a bathroom scale in an elevator with an acceleration of 0.5 meters per second squared.
And that would be up, wouldn't it?
Yeah. Okay, our acceleration is up, which tells us the net force should be up too. And let's go ahead and draw some stuff that we know. Well, first of all, we know that the net force is going to equal the normal force plus the weight, right?
Yep. But we don't have either of those yet. How can we get the weight?
We can get the weight by doing, we know that weight equals mass times gravity, right?
Yep.
So we know what our mass is times gravity, oh yeah, negative 10 meters per second squared. And this gets me negative 4.2 newtons. Okay, so now I have this right here. How can I get the top, the normal force?
I think you got to get the net force first.
I have to get this first, right? Okay, so how can I find my net force?
Newton's second law.
Newton's second law, right? So we've got mass times acceleration. Mass times acceleration. That's what this equals, right?
Yep.
Okay, so I could say mass times acceleration. Oh, this is an ugly spot. I'm going to put it over here. So I'm going to say the force net equals mass times acceleration. My mass is 42 kilograms. What was my acceleration?
0.5 meters per second squared.
0.5 meters per second squared.
That's half.
Half of that's going to be 21 newtons. Okay.
That's going to be a longer arrow or a shorter arrow?
Now, can I just say that you have to remember that we're using Newton's second law right here, right?
Yeah, yes.
Okay. What was your question, Boykin? Oh, the arrow,
Should
right?
the arrow for the normal force be longer or shorter?
The net force is up.
Oh, we really won't know until we do the subtraction.
Oh, yeah. Okay.
You
So
got to
let's
solve
figure it
for
out.
it.
Okay, so how long
But
is this arrow going to be? Let's figure it out.
Should be longer. It's going up.
So this is our force normal. And we know the force normal is, oh, well, what was that equation that we had before? We said force net equals force normal plus the weight, right?
Yeah.
So if we get this by itself,
Got to subtract the weight.
so weight, force net minus weight equals force normal.
Yep.
That's what I want to use. So my force net was
21 newtons.
21 newtons.
Up.
Up, ooh, helpful. Minus the weight, which is always, ooh. Use this color. Which is always down. What was my weight?
42 newtons.
4.2 newtons. Okay.
Hold up. Hold up. It should be 420.
I know, I'm like, that doesn't make sense. Hopefully you're like, Miss Moore. Negative 420.
Damn!
Okay, let's change this. Negative 420 newtons equals, I need a
So when
calculator.
you subtract a negative,
That's going to be a negative number. Oh no, it's going to be positive. I'm sorry. 21 minus a negative 420. 441. Okay, so that's the normal force.
Okay.
Let's draw
What
the
does
arrow.
the scale read? You got all these numbers. It's the normal force.
Scale reads the normal force.
And what's another word for it?
The,
Starts with letter A.
The apparent weight. I was like,
Boy, that's a lot of work.
all right. So you guys have one more question to tackle here. The same person is now going down in the elevator with an acceleration of 0.5 meters per second squared.
Oh, what? Say that again?
Negative.
It's gonna be negative.
What does the scale read? Do it. Let's see what you got.
So it look a lot like that, except the acceleration is down. All right. Is that the end?
I think so. Oh, page 93. Figure 416. What is that?
They can look in their books.
Yeah, check it out. Read through it. See what's going on here.
See, the person's just sitting there. You got a certain amount of weight. When it starts going up, it shows what?
The scale does read a different number. As we go up, it's 1,000, and as it's going down, it's 400, less than 700.
Yep.
And what's going on here? Oh, free fall?
Free fall!
Oh,
my
God! 0.
That's
Okay.
creepy.
And we're done.
Sweet.